Earth Science 11, welcome back to week 6, and we're talking today about hurricanes and tornadoes, some low points in weather. And yes, that is a pun, which you are going to understand soon. So, we have these learning goals for the week. What is a tornado? How are they formed? And how do we classify them? Moving on to hurricanes, what are they? How are they formed? And how are they named? And how are they classified? And we have an optional section, which is how does global warming contribute to much deadlier hurricanes and hurricane season? So, first of all, what is a tornado? Now, on your worksheet, you're going to have question one is a table of a table of properties essentially. So, for example, where tornadoes form versus where hurricanes form. So, this information here is what you're going to need for question one. So tornadoes are much smaller in scale than hurricanes, and they also are land-based. Now, tornadoes can also move over water. These tornadoes are called water spouts. They're generally much weaker than tornadoes, but they are sort of a momentarily water-based tornado. But for the most part, they're going to form over land and they're going to form within storms. The widest they're going to be is around 0.4 kilometers, so that's maybe like a 4 or 5 minute walk kind of a distance in terms of the path of destruction that the bottom of this funnel down here is going to cause. They're very short-lived. Some of them are basically they're between a few minutes or even seconds, and ones that last over an hour are quite rare. You might only get a few of those per year. Now, the winds in a tornado are much stronger than they are in a hurricane. So the winds can be up to 500 kilometers an hour. That's an insanely high speed. Not only does that kill you by tossing you, but even if you were to be able to somehow stand still and resist the force of the winds, think about little rocks and pebbles and pieces of glass that are flying around at 500 kilometers an hour. Even if you could somehow withstand that wind, you really would have a tough time withstanding all those little, basically bullet speed pieces of debris. So they are very deadly winds. There are between 800 to 1,000 tornadoes just in the U.S., although about 75% of the world's tornadoes do occur in the U.S. So no, there's obviously a lot of reasons in there, but the majority of all of the tornadoes in the world are happening in the U.S., and the majority of the tornadoes that happen in the U.S. happen in a place called Tornado Alley. Another reason why tornadoes are quite deadly is because they form quite rapidly. I mean, forecasters can look at some weather conditions and say it's quite likely that a tornado is going to form, but you can't really predict them that far in advance when a tornado is going to form and where it's going to touch down. So on average, forecasters can only give people about a 13-minute warning when there's a tornado advancing. So that's hopefully enough time for you to get to a storm shelter if you lived in Tornado Alley, but not much more than that. So they can be quite deadly for that reason as well. So how are they formed? We're going to watch a video. I'm going to pause it at a few places here, but we're going to watch a video that summarizes quite well. Out of all the videos I saw, this one summarizes it the best. So we're going to quickly watch this video and we'll pause it to give some more details.
Now, while we don't know it all, here's the general idea of how they form.
Let's start in the jet stream. The jet stream is a fast-moving tunnel of air about 25 to 35,000 feet up here in the atmosphere. It's the same height we fly in commercial airplanes. The jet zooms over the Rocky Mountains full of cold air moving at more than 150 and up to 275 miles per hour, rushing over the plains. Meanwhile, down there, warm, moist air is feeding off the Gulf of Mexico, crawling at a slower speed closer to the surface. So that's cold, dry, and fast up here, warm, moist, and slow down there. That difference in wind speed and direction with height is called wind shear. Wind shear then can force a horizontal tube to start rolling in the atmosphere. And now, all you need is a powerful storm tearing across the land to flip that thing vertical and make a tornado. Let me show you. To make a storm, you have rising air, that condensation releasing heat, the heat providing energy that drives what we call updrafts.
So this is where I'm going to pause the video just momentarily for this. So far what we've got here is we've got cold, dry, fast-moving air moving down south from Canada and moving at a high speed. And this meets up with the very slow moving, warm, moist air that's coming in from the Gulf of Mexico heading north. So you got cold air that's fast and high moving south, and then warm, moist air that's south moving north. And this forms the rolling cloud that she talked about. Now, this rolling cloud needs some lifting force to make that rolling motion vertical instead of horizontal. Now, this is usually from the updraft from a storm, which is what she just mentioned there, the updraft, but it could be air moving over a hot part of the earth, some sort of lifting from a fast moving cold front, or even the land itself. But the biggest ones are going to come from a storm. Now, the part that she just briefly mentioned there, which I want to give a bit more detail about, is about how when you have this warm, moist air moving upwards, it provides more energy. Now we know that warm air rises, but it won't rise, all the way into outer space. It rises until it kind of loses it loses that energy. It's not as hot compared to the outside air, and it'll stop rising at that point. However, when you have this warm, moist air that rises and condensation forms, or these air molecules clump together to form raindrops, this releases energy. So I'm going to show this quick diagram here that kind of explains it. So on the left here, you've got water vapor, and this is what it looks like when you have a low relative humidity. So they're not kind of being forced to clump together. And you can see all of these red arrows here. These all represent kind of the motion, or in a sense, they're measuring the energy of these particles. And you can see that all these particles that are separated, they all have energy because they're all moving together. Now, when that warm, moist air starts to cool down, we start to get condensation. So a lot of these droplets, instead of being free moving like they were before, now they're clumped together and not really moving. They're forming these stationary droplets. I mean, they may be drifting slowly, but in general, compared to the individual molecules, they're going much, much slower. So if you look over here on the left side compared to the right side, you can see that there's a lot more arrows on the left side, which means there's a lot more energy of the particles moving around. So when these particles start to condense, then what happens is, in general, there's less energy in the water molecules. Now, water just doesn't disappear. What's happening is that energy that was in the motion of the particles, that's now moving into the air. So what this is doing, when the water vapor condenses, all the energy that was in the moving particles is now going into the air, and that's how the air gets more heat or more thermal energy. So now that it has more thermal energy, that can continue to get the hot air to rise. So we know that the air that was on the surface of the earth was warmer, and so it started to rise. But when this condensation happens, it just gives it more energy, which means it can rise even more. And this is where the updraft comes from, is essentially this continuation of the air continuing to rise because it's taken the energy out of the water molecules into the air molecules, which continues giving enough energy to rise up. Okay, and let's go back to our video.
Then there's this cold, dry air sinking down on the outside of the storm. It's called the rear flank downdraft, or RFD. And that forces a big temperature difference between the storm and the outside environment. So the whole thing itself is rotating. But remember that horizontal roll? Well, now the updraft can actually turn that horizontal tube on its side. And there you have it, a rotating column of air, or as we know it, a tornado.
Okay, so that's just the finale of her video there. So you have this big rolling cloud, but that's not a tornado because it's horizontal, and so you need something to kind of lift up that horizontal rotating cloud into a vertical rotating cloud. And that lifting force to turn it from a horizontal rolling tube of air into a vertical tube of air for the biggest tornadoes comes from these storms. So these storms will come, they have these huge updrafts due to the hot air rising and due to the moisture of the air adding more energy to make it rise even faster, and that leads to this pushing up of this tube of air, and that's how we get tornadoes. Now this is a bit simplified, but that is the best explanation I can give at a grade 11 level, high school level. So yeah, that's a good summary for it. Okay, next one is how do we classify tornadoes? So tornadoes have this Fujita scale or F scale. There's also an EF scale, an enhanced Fujita scale. I'm not going to worry about that. But essentially, it is measured. This scale itself is measured by damage, but it's roughly estimated on the wind speed. So at these types of speeds, if we look at an F5 category tornado, these are the deadliest tornadoes by far. They have incredible damage, even very strong hurricane or tornado resistant houses. So houses that are built to withstand very strong tornadoes. Even the strongest houses can't really stand up to an F5. So they will level off a foundation. They can push a house down the street and just destroy it along the way. They can throw automobiles, throw a car like 100 meters through the air. This is a car being thrown 100 meters through the air. Those are some pretty fast wind speeds. Now, unfortunately, this is in miles per hour, but 300 miles an hour is around 500 kilometers. Trees can have their bark stripped off of them. And again, if you were standing in the path of an F5, you wouldn't be standing there for very long. And most things are just torn apart by all the flying debris. So the flying debris is just as deadly as the wind itself. Yeah, you can get thrown a few hundred meters through the air, but also you'll get torn apart by all the tiny little rocks and pieces of glass that are flying around at 500 miles an hour. Pretty deadly stuff. Okay, now we're moving on to hurricanes. So what is a hurricane? Well, you may have heard other names for a hurricane as well. So in the Northwest Pacific Ocean and the Philippines, they call it a typhoon. In the Indian Ocean and South Pacific, they call it a cyclone. In Australia, they call them willy willies. I don't know why, just because they're Australian, I guess. They like silly names. So hurricanes are different than tornadoes in a number of different ways. So one of them is they form over water as opposed to land. They are way, way bigger. The width of them can be 500 kilometers. So 500 kilometers would be like driving West Van to Whistler, to West Van to Whistler, to West Van, and halfway to Whistler again. This is how wide a tornado can be. I mean, you can see the curvature of the Earth in this picture here, just to give you a scale of how incredibly huge these storms can be. They can last up to 3 weeks, or at least from the start until they finish. The winds are usually less than 300 kilometers an hour, so not quite as fast as a tornado, but still 300 kilometers an hour is pretty bad. There's usually about 10 tropical storms a year in the Atlantic Ocean. And the other thing one thing that makes them a bit less deadly than tornadoes is you can forecast them several days in advance. So typically what will happen is 48 hours before it touches landfall, they'll be giving you a storm watch. So they're saying, keep your eye on the news and watch what's happening. And about 36 hours, they'll give you a storm warning, which is essentially saying there's a good chance you might have to evacuate the city if you live near the coast. But they can change. I mean, Hurricane Katrina was one example where it changed like 9 hours before it touched landfall, it drastically changed direction and changed an increase in intensity. So they are not completely predictable, but definitely a lot more warning than, say, 13 minutes or something like that. So how are these formed? I'm going to watch this video here. I'll just watch it in the picture here.
The formation of a cyclone depends upon the following conditions coinciding. A large, still and warm ocean area with a surface temperature that exceeds 26.5 degrees Celsius over an extended period. This allows a body of warm air to develop above the ocean's surface. Low-altitude winds are also needed to form a tropical cyclone.
So just to pause for a brief moment here, this is why these cyclones form in low pressure areas. So what this narrator just said is that we need to have winds coming in from the side this way to come up and coming in from the side this way. Well, those winds are coming in because these are formed over low pressure areas. If it was a high pressure area, the winds would be going outwards, away from it, and you wouldn't be able to form a tornado. So both hurricanes and tornadoes, well, hurricanes form in low pressure areas, but tornadoes, they create, even if they're not in a low pressure area, they create their own low pressure inside the tornado, for reasons that we won't really get into. So let's carry on with the video.
Air warms over the ocean, it expands, becomes lighter and rises. other local winds blow in to replace the air that has risen, then this air is also warmed and rises. The rising air contains huge amounts of moisture evaporated from the ocean's surface. As it rises, it cools, condensing to form huge clouds about 10 kilometers up in the troposphere. More warm air rushes in and rises, drawn by the draft above. The rising drafts of air carry moisture high into the atmosphere, so that these clouds eventually become very thick and heavy. Condensation then releases the latent heat energy stored in the water vapor, providing the cyclone with more power.
So this is again what I mentioned a few slides ago. When you have that moisture in the air condensing, it loses the moisture itself loses the heat energy as it turns into from a gas to a liquid, but that means that the air itself gains that energy. The energy has to go somewhere. If the water molecules themselves lose the heat energy, then the heat energy gets transferred to the other molecules in the air besides the water vapor. So that leads to it being warmer, and that leads to its ability to rise even higher than it normally would. It's just getting a brand new source of fuel or a brand new source of energy to continue that lifting motion.
This creates a self-sustaining heat cycle. Drawn further upwards by the new release of energy, the clouds can grow to 12 to 15 kilometers high. The force created by the Earth's rotation on a tilted axis, the Coriolis effect, causes rising currents of air to spiral around the center of the tropical cyclone. It is at this stage that the cyclone matures and the eye of the storm is created. As the air rises and cools, some of this dense air descends to form the clear, still eye as the cyclone rages around it. The eye wall, where the wind is strongest, behaves like a whirling cylinder. Cyclones rotate clockwise in the southern hemisphere, anti-clockwise in the northern. The lowest air pressure in a tropical cyclone is always found at the center and is typically 950 millibars or less. The average air pressure at the Earth's surface is about 1010 millibars. Tropical cyclones have significantly lower air pressure than the air that surrounds them. The bigger the pressure difference, the stronger the wind force. One of the lowest air pressures ever recorded was 877 millibars for Typhoon Ida, which hit the Philippines in 1958, where winds reached 300 kilometers an hour. Once formed, the cyclone's movement or track follows a pathway away from its source, driven by global wind circulation. As warm ocean waters feed it heat and moisture, the cyclone continues to enlarge.
Okay, so that summarized it quite well. Again, just to recap, you have these large, calm ocean areas with warm temperatures, and they're centered around a low pressure area. That warm, moist air starts to rise. It releases energy, or the energy from the water vapor condensing gives the air even more energy, allowing it to rise even higher and higher, creating those updrafts. The clouds can reach up to 12 or 15 kilometers high. And because the size of the storm is so massive, the Coriolis effect actually plays an important role in that, and that causes that entire storm to start circulating, like you can see in this picture right here. Oops. And as the storm matures, the eye forms, and that's because they're surrounding the eye is called the eye wall. And all the wind in the eye wall is being forced upwards, and then once it gets to the top, it has to spread itself out, and so you end up getting air that is forced downwards into the middle of the eye of the storm. And because it's downwards moving air, the clouds clear up as we've seen before. So whenever there's air being forced down, it warms it up. It allows it to hold even more moisture than it was before, so it gets lower relative humidity, and therefore it gets clear skies. And essentially what we just saw in that video is the start of a tropical cyclone. A tropical cyclone is essentially just like a baby hurricane. It's just how hurricanes start. As soon as that cyclone gets up to 119 kilometers an hour winds, it just changes its classification to a hurricane. So that's all it is. It's just a hurricane is just a larger tropical cyclone, and now we know how those are formed. So The winds themselves in a hurricane are not actually the most deadly part of a hurricane. In fact, the deadliest aspect is what's called a storm surge, and more than 50% of all hurricane-related deaths are due with the storm surge. And in many hurricanes, that storm surge will result in almost all of the people who are dead are because of this storm surge. So I'm going to just watch this video here that will kind of explain what they look like, and then I'll give you a bit of explanation of how they form.
Flooded conditions. So here's an animation, kind of an explainer of why storm surge happens and how it happens.
Yeah, and it's not just waves, and that's the difference here. So you see waves coming on in, normal sea level right there, but then we get a surge as the eye wall approaches. Not the eye, pretty close to the eye, but with the eye wall, you get a surge where the water rises. The actual level of the sea rises. So there it is rising 3 feet. You still have the waves on top of it. And when you take a level of 3 feet to 5 feet, 6 feet, that water moves inland a long way depending on the lay of the land. And that's why there are some places that will be inundated with water, and then you have the battering waves on top of that. So when you see the video, look at that 12.
So what that video is showing there, just with this picture currently, is when a hurricane comes, it pushes the water in front of it forward. So we know that the water is moving downwards in the eye, and that's essentially forming a bubble where it's pushing against the water. Now, as it's pushing down the water in the middle, when it gets closer to land, there's nowhere for it to go. So that water ends up forming a large kind of hill shape here. Plus there's an issue with pressure. So pressure also adds to it because it's low pressure here. It, in a sense, kind of sucks the water up a little bit as well. Plus you've got the wind moving downwards in here, which ends up pushing the wall of water in front of it. And this whole wall of water, depending on the intensity of the storm, some of them have been recorded as high as 28 feet above the normal sea level, 28 feet higher water. Now this picture here is saying that this purple layer
Plus feet. That's going to be
this purple layer and blue layer here on this screen right around here, not the top one. These two layers are caused by a storm surge. So maybe they're saying that this is a 6-foot tall mountain of water here, as opposed to something larger that could be up to 28 feet. And then on top of that, you now have really high winds, which cause really high waves. So the whole ocean itself has lifted up by about 6 feet, and then you've got 12 feet waves on top of that. You're looking at 18, like when waves are hitting, they're going to be 18 feet higher than they would normally be in sea level. So you can imagine living in that house. The only way you'd be alive in that house is if you're living on the roof, and even then, now you're exposed to the winds. But if you stay inside, you're going to drown. Not a very good place to be, which is why they always try and evacuate people from these coastal cities when a hurricane's on the way. And so that's essentially what I was saying there. These winds are spiraling upwards, but in the eye itself, they're pushing downwards, and this squishes the water outwards and forwards as it moves inland. So as the storm is moving to the right, in this picture here, it's pushing this bubble of water also up and to the right.
What the forecast is on Sanibel right.
Okay, so how are hurricanes named? In case you were curious, this isn't the most important thing, but before a hurricane forms, it's classified as a tropical storm. It's like a baby hurricane. And of course, whenever you have a baby, you've got to give it a name. And so these tropical storms are given names. And you'll notice something here. These are the names for the given season. So the very first tropical storm that we will have in 2020 will be named Arthur, and then Bertha, Cristobal, etc., etc. And so we have these lists, we have 6 different lists of names that are used in rotation. So after 2022, we'll use the 2017 list again after that. So we have these 6 lists of names. They're in alphabetical order. You'll also notice that they alternate between male and female. So Arthur's a male name, Bertha's a female, male, female, male, female. And also by year, they alternate who's going to be first. So in 2020, the first storm of the year will be a male. And in 2021, the first storm of the year will be a female named Anna. Now, for a particularly deadly storm, for a particularly bad hurricane, for example, Katrina, they cross that name off. So in 2020, we have a terrible storm named Faye that ends up killing a lot of people. Well, Faye will be taken out of this list. They'll put in another female F name for the next time this list comes up in 6 years. So there are essentially, when a hurricane name is retired, that's an indication that it was a very deadly storm. And so, yeah, that's how we get our names. And then as they grow into a hurricane, they just change their name. So Hurricane Katrina started off as Tropical Storm Katrina before she got quite bad. And we classify them as well. We also have a 5-point scale. It's called the Saffir-Simpson Hurricane Damage Potential Scale. This one is measured directly from the winds. So these are the winds in kilometers per hour. These are the predicted storm surges. So if it's more than 250 kilometers an hour, you can expect more than 18 feet or more than 5.5 meters of storm surge. And this is the overall damage. So a category 5, you're looking at extensive damage to homes and industrial buildings. You will blow away small buildings, lower floors of structures within 500 meters of the shore, so half a kilometer of the shore. They are going to be damaged if they're not at least 15 feet above sea level. So again, really bad damage in a big hurricane like this. Okay, this part here is about global warming. Feel free to watch this video on your own time. I'm not going to put this in this video here, but if you're looking for the basic idea of why global warming contributes to more severe hurricanes, the answer is that hurricanes get their energy from the energy that's stored in the ocean water. So the ocean water energy transfers to that warm water vapor air energy. And so the more energy the water has, the more energy that water vapor above the ocean is going to have. And the more energy, the bigger that storm is going to be. But feel free to watch this video if you do want to learn a bit more. And then as the optional activity, you can add that note to your worksheet for the week. I hope you've enjoyed it and found this educational. Thank you.